Hello and welcome to Starlit Science. Before we begin tonight's journey, take a moment to like the video and subscribe to the channel if you enjoy calm explorations of the universe and the quiet science that shapes our world. It really helps the channel grow and allows more curious minds to discover these stories. And while you're settling in, I'd love to know, where in the world are you watching or listening from tonight? Are you near the ocean, where the tides quietly rise and fall each day? Or perhaps you're far inland, hundreds of miles from the nearest coastline, yet still just as connected to the same invisible pull that moves the seas. Because whether we live beside a crashing shoreline or in the middle of a quiet city, the same cosmic force is acting on our planet right now. At this very moment, somewhere along Earth's coasts, the ocean is slowly rising. In another place, it is gently retreating. Harbours empty and refill. Shallow shores become wide stretches of sand and then disappear again beneath the water. Salt marshes breathe in and out like the lungs of the planet, and all of it, every tide, every subtle movement of the sea, is guided by something floating silently in the night sky, the moon. From a distance of nearly 384,000 kilometers, the moon exerts a steady gravitational influence over our planet. It does not roar or flash or announce its presence. Instead, it works quietly, pulling on the oceans with a force so subtle that we rarely think about it. Yet that quiet pull moves trillions of tons of water across the surface of Earth every single day. For thousands of years, people noticed this rhythm long before they understood it. Fishermen watched the sea rise and fall beneath the moon's phases. Sailors learned to time their journeys with the tides. Ancient astronomers began to suspect that the glowing disk in the sky might somehow be guiding the oceans below. It was one of the earliest hints that the heavens and the earth are not separate worlds at all. They are connected. Tonight we're going to explore that connection. We'll follow the path of one of the most remarkable relationships in our solar system, the gravitational partnership between Earth and its moon. Along the way, we'll uncover how this distant companion quietly controls the rhythm of the seas, how it has shaped coastlines, ecosystems, and even the length of our days. We'll travel through ancient history, into the mathematics of gravity, across the hidden architecture of the oceans, and outward to tidal worlds elsewhere in the solar system. Because the tides are not just an ocean story, they are a cosmic story. A story about gravity, motion, and the invisible threads that tie our planet to the sky above. So wherever you are tonight, beside the ocean, far from it, or somewhere in between, take a moment to imagine the sea slowly rising and falling somewhere on Earth. Because right now, as you listen, the moon is moving the oceans. If you could step far enough away from Earth to see the entire planet at once, the oceans would not appear still. They would appear to breathe, not quickly and not dramatically, but in slow and deliberate motions that unfold over hours. Vast bodies of water quietly rise, then gradually sink again, as though the planet itself were drawing calm and patient breaths. Along every coastline on Earth, this movement is happening constantly. Water creeps inland across beaches and tidal flats, filling harbours and estuaries, only to retreat again hours later and reveal sandbanks and rocky shorelines that were hidden not long before. This gentle rise and fall of the sea is known as the tide. For people living near the coast, the tides are simply part of everyday life. Boats are tied differently depending on the time of day. Fishermen plan their work around the water level. Shorelines expand and shrink in quiet cycles that repeat again and again. But when we step back and look at the planet as a whole, the tides reveal something remarkable. The oceans are not moving randomly. They are responding to forces that originate far beyond Earth itself. The tide is not just an ocean phenomenon, it is a planetary one. At any given moment, the oceans are being gently stretched by gravity, pulled ever so slightly by a celestial companion that has circled our world for billions of years, the moon. Although it seems distant and quiet in the night sky, the moon exerts a constant gravitational pull on Earth. That pull reaches across the empty space between the two bodies and interacts with our planet in subtle but powerful ways. Gravity, as first formally described by Isaac Newton in the 17th century, is the force through which objects with mass attract one another. Newton showed that every mass in the universe exerts gravitational influence on every other mass. The strength of that attraction depends on two main factors. First, the mass of the objects involved. Second, the distance separating them. The Moon may be much smaller than Earth, but it is still massive enough to exert a noticeable gravitational pull, and because Earth is covered by enormous oceans made of fluid water, those oceans are able to respond to this pull in ways that solid rock cannot. The result is a slow stretching of the oceans. On the side of Earth facing the Moon, the ocean is pulled slightly outward, forming a broad swelling of water. On the opposite side of the planet, another swelling forms due to the combined effects of inertia and the shared orbital motion of Earth and the Moon around their common centre of mass. These two bulges of ocean water circle the planet as Earth rotates beneath them. The result is the familiar rhythm of the tides. Most coastlines experience 2 high tides and 2 low tides within a single lunar day. A lunar day is slightly longer than the 24 hours we normally think of as a day. It lasts about 24 hours and 50 minutes because the Moon is also moving in its orbit while Earth rotates. That extra 50 minutes is why the timing of the tides shifts slightly later each day. It is one of the quiet signatures of the Moon's influence. If Earth had no Moon, the oceans would still move to a small degree under the gravitational influence of the Sun, but the tides would be far weaker and far less dramatic than what we experience today. The Moon is the primary driver of the ocean's rhythm. When scientists study this interaction, they often describe Earth and the Moon as a gravitationally coupled system. This means that the motion of one body influences the other. The two objects are not acting independently, but are instead linked by gravity in a shared orbital dance. In fact, Earth and the Moon do not orbit in the simple way many people imagine. Rather than the Moon circling a perfectly stationary Earth, both bodies move around a shared centre of mass known as the barycenter. This point lies within Earth, but it is not located at the exact centre of the planet. Instead, it sits several thousand kilometres away from Earth's core, along the line that connects Earth and the Moon. As the Moon travels around Earth, both bodies circle this barycenter together. This constant motion contributes to the forces that shape the tides. Understanding the tides therefore requires us to think not only about the oceans, but also about orbital mechanics, planetary motion, and the subtle interplay of gravity between celestial bodies. In other words, the tides are not just a feature of the sea, they are part of astronomy. For much of human history, this connection between the heavens and the oceans remained mysterious. Coastal communities observed tidal cycles for thousands of years, but the mechanism behind them was not fully understood until the development of modern physics. Even after Newton introduced the law of universal gravitation, scientists continued refining their understanding of tidal behaviour. One of the most influential figures in this effort was the oceanographer Walter Munk. Walter Munk spent decades studying the motion of the oceans and is often affectionately called the Einstein of oceanography. His work helped reveal how tides behave not just near coastlines, but across the entire global ocean. Instead of imagining tides as simple bulges following the Moon, Munk and other researchers demonstrated that tides move through ocean basins as complex waves influenced by the shape of continents, the depth of the sea floor, and Earth's rotation. These tidal waves travel thousands of kilometres across the oceans. They bend around continents. They interact with underwater ridges and trenches. They swirl through enormous rotating systems that can span entire ocean basins. In other words, the ocean's breathing is far more intricate than it first appears. What we see along the shore is only the surface expression of a planetary scale process. At this very moment, enormous masses of seawater are slowly shifting around the globe. Trillions of tons of water are being lifted and lowered as Earth rotates beneath the gravitational pull of the Moon. The scale of this movement is difficult to imagine, yet it unfolds so gradually that we rarely notice it happening. Stand on a beach and watch the waterline for a few minutes, and it may appear almost still. But return several hours later and the shoreline will have changed completely. The sea has moved, quietly, patiently, obeying the invisible influence of a distant world hanging in the sky. And this simple observation leads to a deeper question. Just how far does that influence extend? How deeply does the Moon shape the oceans, the planet, and perhaps even the history of life itself? To answer that question, we need to explore not only the tides we see along the shore, but the gravitational partnership between Earth and the Moon that has been shaping our world for billions of years. Long before telescopes, satellites, or the language of modern physics, people living beside the sea noticed something curious about the water. The ocean did not remain in one place. It advanced and retreated with remarkable regularity. Shorelines that appeared wide and open during the morning might be completely submerged by evening. Fishing boats resting on mud at low water would later float again as the sea slowly returned. This pattern repeated day after day. Even without clocks or instruments, the rhythm was obvious to anyone who lived close enough to the coast to watch it. The tides were among the earliest natural cycles that human societies carefully observed. Ancient coastal communities quickly learned that the ocean behaved predictably. The water rose, fell, and rose again in a pattern that could be anticipated. Over time, this knowledge became essential for survival in many maritime cultures. Early fishermen timed their journeys according to the tides because certain fish entered shallow waters only during high water. Traders navigating estuaries waited for incoming tides to carry their boats inland. Harbour builders learned to place docks where vessels could safely rise and fall with the changing sea. This practical knowledge of tides spread quietly across the ancient world. Yet even while people learned to use the tides, the deeper cause behind them remained mysterious. Why should the ocean move at all? Why should the water rise and fall twice each day? And perhaps most intriguing of all, why did these cycles seem to follow the moon? Observers across many early civilizations noticed that the tides appeared strongest during certain phases of the moon. When the moon was full or completely dark, the ocean seemed to rise higher than usual. At other times, the tidal range was smaller. These patterns were subtle, but careful watchers began to recognize them. In the ancient Mediterranean world, one of the first thinkers to seriously consider the connection between the moon and the tides was a Greek astronomer named Seleucus of Seleucia. Seleucus lived during the 2nd century before the Common Era. He was a scholar from the Hellenistic world, a period in which Greek scientific ideas spread across large parts of the eastern Mediterranean and the Near East. Very little of Seleucus's original writing survives today, but later historical accounts tell us something remarkable about his ideas. Seleucus argued that the tides were caused by the moon. For a thinker living more than 2,000 years ago, this was a surprisingly bold proposal. It suggested that events happening in the sky could directly influence the behavior of the oceans on Earth. In modern science, this connection seems obvious, but for ancient observers it was far from simple. At the time, many philosophers believed that the heavens and the earth were governed by completely different rules. The sky was often imagined as a perfect and unchanging realm, while the earth was seen as a chaotic and imperfect place. Seleucus's suggestion quietly challenged that assumption. He proposed that the moon somehow interacted with the ocean, producing the tides that coastal communities observed each day. Although Seleucus could not explain the mechanism behind this interaction, his insight captured an important truth. The motion of the sea was connected to the motion of a celestial body. In other words, the tides were not just an earthly phenomenon, they were astronomical. Similar observations appeared in other cultures as well. Ancient Chinese records from coastal regions describe the timing of tides and their relationship to lunar phases. Early Indian scholars studying astronomy also documented repeating tidal patterns. In the British Isles and along the Atlantic coast of Europe, seafaring communities learned to track tidal cycles with impressive accuracy. In many cases, this knowledge was preserved not in written scientific texts but in oral tradition. Generations of sailors passed down practical rules about when the sea would rise and when it would fall. These traditions allowed people to navigate dangerous coastlines long before formal scientific explanations existed. One might say that early mariners were performing a form of experimental science without realizing it. They carefully observed nature, they recorded patterns, they tested predictions by putting their boats into the water, and through this quiet process of observation and experience, they built a working understanding of the tides. Still, the true explanation remained elusive. For centuries, scholars proposed a variety of theories to explain tidal motion. Some suggested that tides were driven by winds pushing water toward shore. Others imagined hidden channels beneath the ocean floor that filled and emptied like enormous reservoirs. The Roman natural philosopher Pliny the Elder noted the relationship between the moon and the tides in his encyclopedic work Natural History, written during the 1st century of the Common Era. Yet even Pliny could not offer a clear mechanism explaining how the moon influenced the sea. The missing piece was the concept of gravity. Without a scientific understanding of gravitational attraction, the idea that the moon could physically pull on the oceans seemed almost magical. The true explanation required a deeper framework for understanding motion, mass, and force. That framework would not arrive until many centuries later, during a period now known as the Scientific Revolution. During the 17th century, new methods of mathematical analysis and careful experimentation began transforming humanity's understanding of the natural world. Astronomers, physicists, and mathematicians started to uncover universal laws governing both celestial and terrestrial motion. The realization slowly emerged that the same forces shaping the movement of planets could also influence events here on Earth. The tides, once mysterious and unpredictable, were about to become one of the clearest demonstrations of this new understanding. The Moon's connection to the sea, first hinted at by ancient observers like Seleucus, would eventually be explained through a powerful new idea: gravity. For thousands of years, the tides had been observed, recorded, and carefully anticipated by people living beside the sea. Yet the deeper question remained unanswered. What physical force could cause such vast quantities of water to move with such steady rhythm? The answer began to emerge during the 17th century with the work of the English mathematician and physicist Isaac Newton. Newton's ideas transformed humanity's understanding of motion and gravity. In the year 1687, he published a monumental scientific work titled Philosophiae Naturalis Principia Mathematica, often simply called the Principia. Within its pages, Newton introduced a powerful idea that would reshape astronomy, physics, and eventually oceanography. He proposed that every object with mass attracts every other object with mass through a universal force known as gravity. Newton expressed this idea mathematically in what became known as the law of universal gravitation. In words, the relationship can be stated clearly. The gravitational force between two objects equals a constant multiplied by the mass of the first object, multiplied by the mass of the second object, divided by the square of the distance between their centers. Although this equation may sound abstract, its implications were extraordinary. It meant that the same force pulling an apple toward the ground was also guiding the motion of the Moon around Earth and the planets around the Sun. Most importantly for our story, it meant that the Moon must also exert a gravitational pull on Earth. Newton realized that if the Moon's gravity affected Earth, then it must influence the oceans as well. However, the key insight was not simply that the Moon pulls on the oceans. The more subtle point is that gravity acts with slightly different strength across different parts of Earth. This difference arises because gravity becomes weaker with distance. The side of Earth facing the Moon is slightly closer to the Moon than the center of Earth, and the center is slightly closer than the far side of the planet. These distance differences may seem small when compared to the total Earth-Moon separation of roughly 384,000 kilometers, but they are still enough to produce measurable effects. The Moon therefore pulls a little more strongly on the ocean water closest to it, and a little less strongly on water on the far side of Earth. This difference in gravitational strength creates what scientists call a tidal force. Instead of pulling the planet as a whole in one direction, the Moon's gravity stretches Earth slightly along the line connecting the two bodies. The oceans respond to this stretching because water can flow and redistribute itself. The result is the formation of two broad tidal bulges. One bulge forms on the side of Earth facing the Moon, where gravitational attraction is strongest. The second bulge forms on the opposite side of Earth, where inertia associated with the Earth-Moon orbital motion produces a balancing outward effect. These bulges are enormous. They span thousands of kilometers across the ocean surface, yet they are surprisingly shallow, often measuring only a meter or so above the surrounding sea when viewed across the open ocean. Because Earth rotates beneath these bulges, coastlines pass through them over the course of each lunar day. This is why most coastal locations experience 2 high tides and 2 low tides within a cycle, lasting roughly 24 hours and 50 minutes. Newton's theory provided the first clear physical explanation for the tides. The mysterious rise and fall of the ocean could now be understood as the direct result of gravitational interaction between Earth and the Moon. Yet Newton's explanation, while revolutionary, was still incomplete. Newton imagined the oceans responding rather simply to the Moon's pull, forming smooth bulges that moved around the planet as Earth rotated. In reality, the ocean is far more complicated. Earth's oceans are not a single uniform shell of water covering a perfectly smooth sphere. Instead, they occupy irregular basins separated by continents, shaped by underwater ridges, trenches, and vast plateaus. Water moving through these basins behaves more like waves sloshing inside enormous bowls than like a perfectly symmetrical shell. Understanding these complex motions required additional scientific insight. During the late 18th century, a French mathematician named Pierre-Simon Laplace took up the challenge of refining the physics of tides. Laplace was one of the great mathematical minds of his era, and his work extended Newton's gravitational ideas into new territory. While Newton had focused primarily on the gravitational force itself, Laplace explored how oceans behave as moving fluids on a rotating planet. This led him to develop what is now called the dynamic theory of tides. Laplace realized that tides should be understood not just as gravitational stretching, but as waves traveling through ocean basins. These waves are influenced by several factors. First, the gravitational pull of the Moon and the Sun provides the energy that drives tidal motion. Second, Earth's rotation affects how water moves across the surface through a phenomenon known as the Coriolis effect. This effect causes moving fluids to curve slightly as they travel across a rotating planet. Third, the shape and depth of the ocean basins themselves determine how tidal waves propagate, reflect, and sometimes amplify. To describe these processes mathematically, Laplace derived a set of equations governing fluid motion on a rotating sphere. These equations, now known as Laplace's tidal equations, remain fundamental to the study of ocean dynamics. Modern oceanographers still rely on mathematical frameworks that descend directly from Laplace's work. When scientists today build computer models of global tides, they incorporate many of the same principles Laplace identified more than 2 centuries ago. What these models reveal is that tides are not simply bulges following the Moon. Instead, the tides behave as large-scale oscillations of entire ocean basins. Water moves through these basins in enormous rotating wave patterns. Some tidal waves travel thousands of kilometers across the oceans, bending around continents and interacting with underwater landscapes. In certain regions, these motions create remarkable patterns known as amphidromic systems, where tides rotate around central points in the ocean. In other places, resonance within ocean basins can amplify tidal ranges dramatically, producing some of the highest tides on Earth. The simple rise and fall observed along the shoreline is therefore only a small part of a much larger system. The oceans are constantly in motion, responding not only to the Moon's gravity but also to the shape of the planet itself. Seen from this perspective, the tides become something far more impressive than a coastal curiosity. They are the visible expression of planetary-scale physics. Trillions of tons of seawater are shifting across the globe in response to gravitational forces and the rotation of Earth. The patterns formed by these movements reflect the geometry of ocean basins, the distribution of continents, and the subtle influence of celestial bodies orbiting high above. And at the heart of all of this motion lies a remarkable partnership between 2 worlds. Earth and the Moon are bound together by gravity, orbiting a shared center of mass and continually influencing one another. To truly understand the tides, we must look more closely at this relationship, because the geometry of the Earth-Moon system plays a crucial role in shaping the rhythm of the sea. When we look up at the Moon, it often feels as though it is quietly circling Earth like a loyal companion. The image is simple and comforting. Earth sits at the center, and the Moon travels around it in a steady orbit, returning to the same phases month after month. But the true motion of the Earth and the Moon is slightly more subtle and far more interesting. In reality, the Moon does not orbit a perfectly stationary Earth. Instead, both bodies move together around a shared point in space known as the barycenter. A barycenter is the center of mass of a 2-body system. It is the point around which both objects orbit as they respond to each other's gravitational pull. For the Earth-Moon system, this barycenter lies inside Earth itself, but it is not located exactly at the planet's center. Instead, it sits roughly 4,600 kilometers away from the center of Earth, along the line connecting Earth and the Moon. To put that distance into perspective, Earth's radius is about 6,370 kilometers. That means the barycenter lies deep within the planet, yet clearly offset from the center. This offset means Earth performs a small but continuous wobble as the Moon moves through its orbit. While the Moon travels around Earth once every 27 1/3 days, Earth also traces a gentle circular motion around the same barycenter. Both bodies are effectively dancing around this shared center of mass. It is a slow gravitational partnership, and like many good partnerships, neither participant remains perfectly still. This shared motion contributes to the forces that shape the tides. To understand how, it helps to imagine the Earth-Moon system as a rotating pair. As the 2 bodies circle their barycenter, every part of Earth experiences a combination of gravitational attraction toward the Moon and an outward inertial effect associated with the orbital motion of the system. The balance between these effects produces the familiar tidal forces that stretch Earth's oceans. On the side of Earth facing the Moon's gravitational pull is slightly stronger because that part of the planet is closer to the Moon. The ocean there is gently drawn outward, forming one of the tidal bulges. On the opposite side of the planet, something interesting happens. The gravitational pull of the Moon is weaker there because that side is farther away. Meanwhile, the inertial effect associated with the orbital motion of the Earth-Moon pair remains roughly the same across the entire planet. The result is that water on the far side is also displaced outward, creating the second tidal bulge. These two bulges lie roughly along the line connecting Earth and the Moon. As Earth rotates beneath them, different parts of the planet pass through these regions of elevated water, producing the cycle of high and low tides experienced along coastlines. The mechanism may sound complex, but the principle behind it is straightforward. Tides arise from differences in gravitational pull across Earth's diameter. That difference stretches the oceans very slightly, creating the slow planetary breathing we observe along the shores. What makes this phenomenon especially fascinating is that it is not unique to Earth. The same gravitational physics operates throughout the solar system and far beyond it. Planetary scientists study these interactions under the broader field known as tidal dynamics. One of the researchers who helped develop modern understanding of tidal behavior in planetary systems is the American planetary dynamicist Peter Goldreich. Goldreich spent much of his career examining how gravity shapes the motion and evolution of celestial bodies. His work explored how tidal forces influence the orbits, rotations, and internal heating of planets and moons. One of the most striking examples of tidal influence is the phenomenon known as tidal locking. Tidal locking occurs when the rotation of one celestial body becomes synchronized with its orbital period around another body. When this happens, the same side of the smaller body always faces the larger one. The Moon provides a familiar example. From Earth, we always see essentially the same lunar hemisphere. The far side of the Moon remained unseen by human eyes until spacecraft first photographed it in the 20th century. This occurs because the Moon rotates on its axis in exactly the same amount of time that it takes to orbit Earth. Both motions take about 27 1/3 days. As a result, the same lunar face always points toward Earth. Tidal locking develops gradually over long periods of time. Early in its history, the Moon likely rotated more quickly. However, tidal forces between Earth and the Moon created internal friction within the Moon's interior. Over millions of years, this friction slowed the Moon's rotation until it became synchronized with its orbit. The process is gentle but persistent. Gravity rarely rushes. Instead, it works slowly across immense spans of time. The concept of tidal locking is not limited to the Earth-Moon system. Many moons in the solar system are tidally locked to their parent planets. The large moons of Jupiter and Saturn, including Europa, Ganymede, and Titan, all show the same hemisphere to their host planets. Even some planets outside our solar system may be tidally locked to their stars. Astronomers studying exoplanets have discovered worlds orbiting very close to their stars where one side of the planet may experience permanent daylight, while the other side remains in eternal night. These extreme environments arise from the same gravitational principles that produce Earth's tides. This broader perspective reveals something profound. Tidal physics is not just an ocean phenomenon. It is a universal mechanism through which gravity reshapes the motion of worlds. On Earth, tides move the oceans. On Jupiter's moon Io, tidal forces generate enormous internal heating that drives spectacular volcanic eruptions. Io is the most volcanically active body in the solar system because gravitational tides continually flex its interior. On Saturn's moon, Enceladus, tidal forces help maintain a hidden ocean beneath an icy crust, occasionally venting water vapor and ice particles into space through towering plumes. Across the cosmos, gravity stretches, compresses, and reshapes celestial bodies in countless ways. The tides of Earth are simply one example of this larger story. What makes our planet unique is the presence of vast oceans capable of responding visibly to these forces. Water moves easily. It flows, rises, and falls in response to the smallest gravitational differences. Rock and metal respond much more slowly, though even Earth's solid crust experiences tiny tidal deformations known as Earth tides. The oceans, however, make the process visible. They turn gravitational physics into something we can observe directly along beaches, bays, and estuaries. Yet even with this understanding, the picture remains incomplete, because while the moon provides the driving force behind the tides, the way those tides behave across the globe depends strongly on another factor: the shape of the ocean basins themselves. The continents, the depths of the seafloor, and the geometry of Earth's rotating surface all influence how tidal waves move through the oceans. And that complexity adds another layer to the story of the sea's quiet motion. If the moon simply pulled on a perfectly smooth ocean covering a perfectly round Earth, the tides would behave in a very simple way. Two enormous bulges of water would slowly circle the planet as Earth rotated beneath them. Every coastline would experience tides of roughly similar size, rising and falling with steady regularity. But Earth is not a smooth sphere, and the oceans are not evenly distributed across its surface. Instead, the water of our planet occupies a set of enormous, irregular basins shaped by continents, mountain ranges beneath the sea, deep trenches, broad continental shelves, and countless other geological features. This complex architecture changes how the tides behave. Rather than moving as simple bulges following the moon, the tides travel through the oceans as large-scale waves. These waves interact with the shape of the ocean basins in ways that can redirect, amplify, or even cancel tidal motion. In other words, the moon provides the driving force, but the shape of Earth determines how that force is expressed in the oceans. To understand this idea more clearly, it helps to imagine the difference between shaking water inside two containers. If you move a perfectly round bowl filled with water, the liquid may slosh in a relatively simple pattern. But if the container has narrow channels, irregular walls, or deep pockets, the water inside behaves very differently. Some waves reflect from the sides, others become trapped in smaller regions. Some motions grow stronger when the timing of the shaking matches the natural rhythm of the water inside the container. The oceans behave in a similar way. They are enormous basins connected by narrow passages and shaped by geological structures that extend across thousands of kilometers. Because of this complexity, tidal motion is influenced not only by gravity, but also by the geography of the seafloor. This field of study belongs to physical oceanography, the branch of science that examines how water moves through the global ocean. One of the scientists who made important contributions to understanding large-scale ocean motion is Carl Wunsch. Carl Wunsch is a physical oceanographer associated with the Massachusetts Institute of Technology. His research has explored how ocean circulation operates across entire basins, including the role that tides play in distributing energy through the seas. Wunsch and other oceanographers helped show that tidal motion is not confined to coastlines. Instead, tidal energy moves across the entire ocean system, interacting with underwater landscapes in complex ways. When tidal forces set water in motion, the resulting waves travel across ocean basins. These waves can be hundreds or even thousands of kilometers wide, yet their vertical height across the open ocean is usually small, often measuring less than a meter. This is one reason tides are not very noticeable in the deep ocean. Far from land, the surface of the sea may rise and fall only slightly as tidal waves pass beneath ships. But as those waves encounter continental shelves and coastal boundaries, the situation changes. A continental shelf is the relatively shallow region of ocean floor that extends outward from the edges of continents before dropping into the deeper ocean. Many shelves are only a few hundred meters deep, compared with several thousand meters in the open ocean. When tidal waves move from deep water onto these shallower shelves, the waves slow down. At the same time, the energy carried by the wave becomes compressed into a smaller vertical space. The result is an increase in tidal height. This is why tides are often much larger near coastlines than in the open sea. In certain locations, the shape of the coastline and seafloor can amplify this effect dramatically. Narrow bays or funnel-shaped estuaries can concentrate tidal motion, causing water levels to rise many meters during each cycle. One famous example is the Bay of Fundy, located between the Canadian provinces of Nova Scotia and New Brunswick. The geography of this region allows tidal waves entering the bay to resonate with the natural oscillation of the basin, producing tidal ranges that can exceed 15 meters. That is roughly the height of a 4-story building. Such dramatic tides illustrate how the structure of ocean basins controls the movement of water. Underwater mountain ranges also influence tidal behavior. The mid-ocean ridges that run through many parts of the global ocean act like barriers and channels for moving water. As tidal waves encounter these ridges, part of their energy may be reflected or redirected. Deep ocean trenches can guide currents in other directions, while island chains create obstacles that reshape the flow of water. All of these features interact with tidal waves as they move through the oceans. The result is that tides do not simply move in a straight line across the planet. Instead, they often travel in rotating patterns shaped by Earth's rotation and the geometry of the basins themselves. Because Earth is spinning, moving water experiences a subtle deflection known as the Coriolis effect. This effect causes moving fluids in the northern hemisphere to curve slightly to the right and fluids in the southern hemisphere to curve slightly to the left. Although this deflection is small at any given moment, it becomes significant when large bodies of water move across entire ocean basins. Over time, tidal waves can organize into vast rotating systems. In these systems, water does not simply move toward the shore and then back out again. Instead, the tidal wave circulates around a central region, much like a slow-moving whirlpool spanning hundreds or even thousands of kilometers. Within these rotating patterns, something remarkable occurs. There are certain points in the ocean where the tidal range becomes extremely small. At these locations, the height of the tide may barely change at all. These special points act as the centers around which the tidal waves rotate. Oceanographers call them amphidromic points. The word amphidromic comes from Greek roots meaning around a turning point. It describes exactly what happens in these tidal systems. Water levels rise and fall as tidal waves rotate around the amphidromic center, but at the center itself the vertical motion is minimal. Several amphidromic systems exist across the world's oceans. In the North Atlantic Ocean, for example, large rotating tidal patterns govern the motion of water across the basin. Similar systems appear in the Pacific Ocean and the Indian Ocean. Each basin has its own unique tidal geometry, shaped by the arrangement of continents and the depth of the seafloor. This means that the Moon's gravitational pull does not produce identical tides everywhere. Instead, the tides we observe depend on how gravitational forces interact with the complex architecture of Earth's oceans. The Moon provides the steady rhythm. The oceans interpret that rhythm in their own distinctive ways. Understanding these patterns required centuries of observation, improved mathematical models, and detailed measurements of the seafloor. Yet even with all this knowledge, the motion of the tide still carries a sense of quiet elegance. Gravity pulls, the oceans respond, and the shape of the planet determines how that response unfolds. But the rotating tidal systems described here are only the beginning of the story. Because once scientists recognized these patterns, they began to notice something even more intriguing about the way tides move across the ocean. If someone were able to watch the tides across an entire ocean basin from high above the planet, the pattern would look surprisingly elegant. Instead of water simply moving toward shore and then retreating again in straight lines, the ocean would appear to rotate in vast circular motions. These rotating patterns form one of the most fascinating structures in ocean dynamics, and they revolve around special locations known as amphidromic points. An amphidromic point is a place in the ocean where the tidal range becomes extremely small. In some cases, the change in water height at these points is so slight that the tide may appear almost non-existent. Yet the surrounding ocean is very much in motion. Water levels rise and fall in sweeping circular waves that rotate around these central locations. As the tidal wave travels around the amphidromic point, different regions of the ocean experience high tide at different times. The result is a rotating tidal system that spans enormous distances. In the North Atlantic Ocean, for example, the tidal wave circulates around amphidromic points, in patterns that cover thousands of kilometers. Similar rotating systems exist in the Pacific Ocean and the Indian Ocean. Each of these systems functions like a slow-moving wheel of water. Near the center of the wheel, the water hardly moves vertically at all. Farther from the center, the tides grow progressively stronger, rising and falling more dramatically along distant coastlines. This is one of the reasons why tidal ranges vary so dramatically around the world. Some coastlines experience only modest changes in water level, sometimes less than a meter between low and high tide. Other regions see enormous tidal swings, where the ocean may rise or fall more than 10 meters during a single cycle. These differences are not caused by variations in the Moon's gravity. The Moon pulls on the entire planet with nearly the same force. Instead, the differences arise from how tidal waves move through the ocean basins, and how those waves rotate around amphidromic points. Understanding these patterns required careful observation and mathematical analysis. One of the scientists who made important contributions to this field was the British oceanographer Joseph Proudman. Joseph Proudman worked during the early 20th century and helped establish modern research into tidal dynamics. His work focused on how tides behave as waves travelling through rotating ocean basins. Proudman recognized that tidal motion could be described using the principles of fluid dynamics combined with the effects of Earth's rotation. In 1921, he became the founding director of the Liverpool Tidal Institute in England. This institute later evolved into what is now known as the National Oceanography Centre, a major research organisation studying ocean processes. Through mathematical analysis and observational data, Proudman and his colleagues explored how tidal waves interact with the geometry of ocean basins. Their work helped clarify why amphidromic systems appear in specific locations across the globe. A crucial factor shaping these systems is the rotation of Earth. Because Earth spins on its axis once every 24 hours, moving water experiences a subtle deflection known as the Coriolis effect. The Coriolis effect arises because different parts of the rotating planet move at different speeds. Near the equator, the surface of Earth travels faster than it does near the poles. When water begins to move across this rotating surface, its path appears to curve relative to the ground beneath it. In the northern hemisphere, moving water tends to curve slightly to the right. In the southern hemisphere, the deflection occurs in the opposite direction, causing water to curve slightly to the left. Although the effect is small at any given moment, it becomes significant when tidal waves travel across large distances. As tidal waves propagate through ocean basins, the Coriolis effect gradually bends their paths. Combined with the boundaries created by continents and seafloor features, this bending causes tidal waves to organize into rotating systems. The rotation around amphidromic points follows a predictable direction depending on the hemisphere. In the northern hemisphere, tidal waves typically rotate in a counterclockwise direction around amphidromic centers. In the southern hemisphere, the rotation tends to occur clockwise. This pattern emerges naturally from the interaction between gravity, ocean basin geometry, and the rotating frame of Earth. Oceanographers often visualize these rotating tidal patterns using maps called cotidal charts. A cotidal chart displays lines connecting locations that experience high tide at the same moment. When these lines are drawn across entire ocean basins, they form sweeping spirals that wrap around amphidromic points. The spiraling pattern clearly reveals the rotating motion of tidal waves. Seen from space in slow motion, the oceans would appear to pulse and swirl as tidal waves travel around the planet. It is a graceful choreography shaped by gravity and planetary rotation, and yet, despite this complexity, the system remains remarkably predictable. The timing of tides can be forecast years in advance with extraordinary accuracy. Coastal tide tables rely on mathematical models that incorporate lunar motion, Earth's rotation, and the geometry of ocean basins. These predictions are vital for navigation, harbour management, coastal engineering, and marine ecosystems. Ships entering shallow ports often depend on precise tidal timing to avoid running aground. Fishing communities rely on tidal cycles to anticipate the movement of marine life. Even certain coastal plants and animals synchronize their life cycles with tidal rhythms. All of this activity depends on the predictable behavior of rotating tidal systems. But while amphidromic patterns explain much about the movement of tides across Earth's oceans, another important influence remains in the story. The Moon is not the only celestial body exerting gravitational forces on our planet. Far beyond the Moon, another massive object also pulls on Earth's oceans, the Sun. Although the Sun lies much farther away, its immense mass allows it to exert a measurable gravitational influence on the tides. And when the gravitational effects of the Sun combine with those of the Moon, the rhythm of the ocean gains another layer of complexity. Although the Moon is the primary driver of Earth's tides, it is not the only celestial body pulling on our oceans. Far beyond the Moon, at a distance of roughly 150 million kilometers, lies the Sun. The Sun's gravitational pull extends across the entire solar system, guiding the orbits of planets, comets, and asteroids. That same pull also reaches Earth's oceans. At first, this may seem surprising. The Moon is so much closer to Earth than the Sun that it feels natural to assume it must dominate tidal motion completely. Yet gravity depends not only on distance, but also on mass. The Sun contains more than 99% of the total mass in the solar system. It is so massive that its gravitational influence easily holds the planets in orbit across billions of kilometers of space. Even from its great distance, the Sun exerts a noticeable gravitational force on Earth, However, when it comes to tides, distance plays an especially important role. Tidal forces depend on differences in gravitational pull across an object. Because the Moon is much closer to Earth than the Sun, the difference in the Moon's gravitational strength between the near side and far side of Earth is greater. For this reason, the Moon produces tides that are more than twice as strong as those generated by the Sun. Even so, the Sun's contribution is far from insignificant. When the Sun's tidal influence combines with the Moon's, the result is a complex three-body gravitational interaction involving Earth, the Moon, and the Sun. This interaction produces one of the most recognizable patterns in tidal behavior. At certain times during the lunar month, the gravitational forces of the Moon and the Sun align in a way that reinforces each other. When this happens, the tidal range becomes larger than usual. These enhanced tides are known as spring tides. Despite the name, spring tides have nothing to do with the season of spring. The term spring refers to the idea of water springing upward or rising higher than normal. Spring tides occur during two phases of the Moon. The first occurs when the Moon is new, positioned between Earth and the Sun. In this arrangement, the gravitational pull of the Moon and the Sun acts in roughly the same direction. The second occurs when the Moon is full, located on the opposite side of Earth from the Sun. In that case, the gravitational forces still line up along the same straight line through Earth. In both situations, the tidal forces of the Moon and the Sun combine. The result is a larger difference between high tide and low tide. During spring tides, high tides rise slightly higher and low tides fall slightly lower. Coastal communities often notice these changes clearly. Harbours may fill more completely than usual, while exposed shorelines during low tide stretch farther than normal across beaches and tidal flats. But the alignment between the Moon and the Sun does not remain constant. As the Moon continues along its orbit, it gradually moves into positions where the gravitational forces of the two bodies no longer reinforce one another so strongly. Roughly 1 week after a spring tide, the Moon reaches what astronomers call the first quarter phase. In this position, the Moon lies roughly 90 degrees away from the line connecting Earth and the Sun. Now, the gravitational pull of the Moon acts in a direction that partially offsets the Sun's tidal influence. The result is a smaller tidal range. These weaker tides are called neap tides. During a neap tide, high tides are not as high and low tides are not as low. The difference between them becomes more moderate. About a week later, when the Moon reaches the third quarter phase, the same geometry appears again, producing another period of neap tides. The entire pattern repeats roughly every 14 to 15 days. This repeating rhythm forms what scientists call the fortnightly tidal cycle. The word fortnight simply means 14 nights, an Old English term still used in certain scientific contexts. The cycle reflects the changing geometry between Earth, the Moon, and the Sun as the Moon completes its orbit around Earth. Understanding these gravitational relationships belongs to a branch of physics known as celestial mechanics. Celestial mechanics studies how objects move under the influence of gravity. It provides the mathematical tools needed to analyze the interactions between multiple bodies in space. One scientist who made important contributions to this field was Victor Szebehely. Victor Szebehely was a Hungarian-American mathematician who specialized in what is known as the three-body problem. This problem concerns predicting the motion of three gravitationally interacting bodies, such as Earth, the Moon, and the Sun. The three-body problem is famously complex. While the motion of two bodies interacting through gravity can be calculated precisely, adding a third body introduces mathematical complications that can produce intricate and sometimes chaotic behavior. Szebehely's work helped clarify how such systems behave over long periods of time, and his research remains influential in the study of orbital mechanics. In the case of Earth's tides, the interaction between three bodies does not produce chaos, but it does generate subtle variations in tidal strength. These variations shape the fortnightly rhythm of spring tides and neap tides observed along coastlines across the planet. For coastal ecosystems and human activities, this repeating cycle plays an important role. Certain marine animals time their spawning to coincide with the stronger currents associated with spring tides. Fishermen often plan their work according to the expected tidal range. Coastal engineers must consider these cycles when designing harbours, bridges, and sea defences. All of these patterns arise from the quiet gravitational negotiation between three celestial bodies. Earth rotates, the Moon orbits, the Sun exerts its distant pull, and the oceans respond. As remarkable as these cycles are, they reveal only part of the story, because tides are not merely the movement of water up and down along shorelines. Beneath the surface, enormous quantities of energy are being transferred through the oceans. Tidal forces move trillions of tons of seawater across the globe every day. Understanding what happens to that energy reveals another hidden dimension of the ocean's motion. Every time the tides rise and fall, an enormous amount of energy is quietly moving through the oceans. It is easy to overlook this fact because the motion often appears gentle. The shoreline creeps inland, then slowly retreats. Harbours fill and empty. Coastal rocks disappear beneath the water and later reappear again. Yet beneath that calm rhythm lies a vast transfer of energy driven by gravity. The moon and the sun are continuously pulling on Earth's oceans. In response, immense quantities of seawater shift across the planet. Scientists estimate that the power involved in global tidal motion amounts to several trillion watts. That is comparable to the combined output of thousands of large power stations. Most of this energy does not appear as dramatic waves crashing against coastlines. Instead, it moves quietly through the ocean as broad tidal currents and long wavelength waves that travel across entire basins. In the open ocean, tidal motion can span thousands of kilometers while rising and falling only a small distance at the surface. But what happens to this energy after it begins moving through the water? Part of the answer lies in a remarkable phenomenon hidden far below the surface of the sea. These are internal tides. To understand internal tides, it helps to think about the structure of the ocean itself. Although the ocean may appear uniform when viewed from above, it is actually layered. Differences in temperature and salinity create variations in water density. Warmer, lighter water often lies above colder, denser water, forming layers that resist mixing. Oceanographers refer to this layering as stratification. Because of this structure, waves can form not only on the surface of the ocean, but also along the boundaries between layers of different density. These deep waves are called internal waves. Unlike surface waves, which move along the interface between water and air, internal waves travel along density boundaries within the ocean itself. Some of these waves can reach heights of tens or even hundreds of meters, yet remain completely invisible from the surface. The movement of tides across underwater landscapes can generate these deep waves. When tidal currents flow across features such as underwater mountain ranges, ridges, and seamounts, the moving water is forced upward and downward along the contours of the seafloor. This motion disturbs the density layers within the ocean and creates internal tidal waves. These waves propagate through the ocean's interior, sometimes traveling hundreds or even thousands of kilometers away from their source. The existence of these deep waves was once difficult to observe directly. However, advances in oceanographic instruments and satellite measurements have revealed that internal tides are widespread across the global ocean. Understanding their behavior became a major focus of oceanographic research during the 20th century. One influential contribution came from the work of Walter Munk and Carl Garrett. Together they developed what is known as the Garrett-Munk theory. This theory describes the statistical distribution of internal waves throughout the ocean. It provides a mathematical framework explaining how energy moves through these waves and how they contribute to mixing in the deep sea. Although the Garrett-Munk model involves detailed mathematics, the central idea is quite intuitive. The ocean is filled with internal waves generated by tidal motion and other forces. These waves move energy throughout the water column, gradually breaking and mixing the ocean layers. When internal waves break, much like surface waves breaking along a beach, they cause turbulence. This turbulence allows water from different depths to mix together. That mixing plays a crucial role in regulating the ocean's structure. Without mixing, the deep ocean would remain extremely stable and layered, with very little exchange between surface and deep water. Over long periods of time, this could disrupt the circulation patterns that help distribute heat around the planet. Instead, internal tides provide a constant source of energy that stirs the ocean slowly but persistently. This mixing helps transport nutrients upward from deep waters toward the surface. Many marine ecosystems depend on this process. Microscopic organisms known as phytoplankton thrive in sunlit surface waters when nutrients are available. These tiny organisms form the base of the marine food web, supporting fish, marine mammals, and countless other species. In this way, the hidden motion of internal tides contributes indirectly to life throughout the oceans. The mixing also influences Earth's climate system. ocean circulation carries heat from equatorial regions toward the poles, helping regulate global temperature patterns. Internal tidal mixing plays a subtle but important role in maintaining these circulation systems. Even though the process occurs deep beneath the ocean surface, its effects ripple outward across the entire planet. Many internal tides originate near underwater mountain ranges. The mid-ocean ridges, which form the longest mountain chains on Earth, stretch for tens of thousands of kilometers across the ocean floor. When tidal currents encounter these ridges, enormous internal waves can form and radiate outward into the deep ocean. Other sources include isolated seamounts, steep continental slopes, and island chains that disrupt tidal flows. In certain regions, scientists have observed internal waves hundreds of meters tall traveling slowly through the depths. From the surface, the ocean may appear calm, yet far below, great underwater waves are passing silently through the darkness. These hidden motions remind us that the tides are far more than the rise and fall of water along a beach. They are part of a vast planetary system transferring energy across the oceans every day. And this system has been operating for a very long time. The gravitational partnership between Earth and the Moon did not begin recently. It has been shaping the movement of the oceans for billions of years. In fact, the tides of the distant past may have been very different from the ones we experience today. Because the relationship between Earth and the Moon has slowly evolved over immense stretches of geological time. The tides we experience today feel steady and familiar. The ocean rises and falls by a few meters along most coastlines, and the timing of those changes follows a rhythm that has become part of daily life for many communities around the world. But the tides have not always looked the way they do now. If we could travel backward through time to the early history of Earth, the oceans would behave very differently. The reason lies in the changing distance between Earth and the Moon. To understand how that distance evolved, we need to begin with the origin of the Moon itself. For much of human history, the Moon's formation remained a mystery. Early ideas range from the Moon forming alongside Earth to the possibility that it had been captured by Earth's gravity long after the planet formed. During the 20th century, scientists began developing a new explanation that eventually became the leading theory. This is known as the giant impact hypothesis. The giant impact hypothesis proposes that the Moon formed from debris created when a young Earth collided with another planetary body roughly the size of Mars. The hypothetical impactor is often referred to as Theia. According to this theory, the collision occurred more than 4 billion years ago, during the early chaotic era of the solar system, when large bodies frequently collided while planets were still forming. When Theia struck Earth, the impact would have released an extraordinary amount of energy. The collision likely vaporized large portions of both bodies and blasted enormous quantities of molten rock into orbit around Earth. Over time, this debris began to gather together through gravitational attraction. Gradually the fragments merged and cooled, eventually forming the Moon. The giant impact hypothesis was developed in the 1970s by scientists including William K. Hartmann and Donald Davis. Their work provided a framework that explained several unusual features of the Earth-Moon system. One of those features is the unusually large size of the Moon compared with its host planet. Most planetary moons in the solar system are tiny compared with the planets they orbit. Our Moon, however, is relatively large, measuring about 1/4 the diameter of Earth. Another clue comes from the composition of lunar rocks. Samples collected by astronauts during the Apollo missions showed that the Moon's material is remarkably similar to the outer layers of Earth. This supports the idea that the Moon formed from debris originating from Earth's mantle. Over the decades, additional evidence has strengthened the giant impact hypothesis. Computer simulations have shown that collisions between young planetary bodies can produce disks of debris capable of forming moons. These simulations have become increasingly sophisticated thanks to advances in computing power. One scientist who has played a major role in this work is planetary scientist Robin Canup. Robin Canup has conducted extensive research into the formation of the Moon using detailed numerical models. Her simulations explore how material from a giant impact could have coalesced into a stable lunar orbit. These models suggest that the newly formed Moon would initially have orbited Earth at a much smaller distance than it does today. Instead of sitting nearly 400,000 kilometers away, the early Moon may have been only 20,000 to 30,000 kilometers from Earth. That difference might not sound enormous on a cosmic scale, but it would have had dramatic consequences for the tides. Because tidal forces depend strongly on distance. The strength of tidal forces varies approximately with the cube, of the distance between two bodies. In simpler terms, if the moon moves twice as far away, its tidal influence becomes roughly 8 times weaker. This means that when the moon orbited much closer to Earth, the tides would have been vastly stronger than they are today. Imagine standing on an ancient shoreline billions of years ago. Instead of tides rising by a meter or two, the ocean might have surged upward by tens of meters during each cycle. Vast volumes of water would sweep across coastal landscapes, then retreat again hours later. These tides would not only be higher, but also faster moving. The moon would have appeared much larger in the sky as well, possibly several times its current apparent size. It would dominate the night sky, looming overhead as it orbited rapidly around the young Earth. Over long periods of time, however, this dramatic arrangement gradually changed. The tides themselves played a role in this transformation. As tidal forces move water across the ocean basins, friction occurs between the moving water and the seafloor. This friction converts a small portion of tidal energy into heat. The loss of energy slightly slows Earth's rotation while transferring angular momentum to the moon's orbit. The result is that the moon slowly moves farther away from Earth. This process continues today. Measurements made using laser reflectors left on the moon during the Apollo missions show that the moon is receding from Earth at a rate of about 3.8 centimeters each year. That distance is roughly the width of a fingernail growing over the course of a year. Slow, but relentless. Over billions of years, that gradual outward drift has significantly reduced the strength of Earth's tides. Yet during the early history of the planet, when the moon was closer and tides were stronger, those powerful tidal forces may have shaped the surface of Earth in important ways. Ancient coastlines likely experienced intense cycles of flooding and exposure as enormous tidal waves swept across the young planet's shores. These repeating movements could carve channels, redistribute sediments, and create complex networks of tidal flats and lagoons. In geological terms, these environments would be dynamic and constantly changing. Some scientists believe that such environments may have played an important role in the early development of life on Earth, because tidal regions naturally create cycles of wetting and drying, concentration and dilution, and those cycles can have profound effects on chemistry. When scientists try to understand how life began on Earth, they often begin with a deceptively simple question. How did simple molecules become something capable of metabolism, replication, and evolution? The earliest living systems were not complex plants or animals. They were microscopic chemical structures, probably little more than collections of organic molecules interacting in the right environment. But the key phrase there is the right environment. Life requires energy, chemical building blocks, and conditions that allow those ingredients to interact repeatedly over long periods of time. The environment must be stable enough to sustain chemical reactions, yet dynamic enough to encourage new combinations of molecules. Some researchers believe that tidal environments may have provided exactly that kind of setting. Billions of years ago, the young Earth likely possessed coastlines dotted with shallow pools, lagoons, and tidal flats. These areas would regularly flood and drain as the tides advanced and retreated. Unlike the open ocean, where water remains relatively constant, tidal zones experience continuous change. Water flows in, water flows out. Pools fill, pools evaporate, and then the entire process repeats again. These repeating cycles create what scientists call fluctuating chemical environments. A fluctuating environment is one where temperature, salinity, concentration of chemicals, and water levels change regularly. Such variations can drive chemical reactions that might otherwise proceed very slowly or not at all. For example, imagine a shallow tidal pool on an early shoreline. As the tide rises, the pool fills with seawater carrying dissolved minerals and organic molecules. Sunlight warms the water, and chemical reactions begin to occur among the molecules present. Later, when the tide retreats, the water level drops, and some of the liquid evaporates under the heat of the sun. Evaporation concentrates the dissolved substances left behind. Molecules that were previously far apart now become more crowded together, and when molecules crowd together, the chances of them interacting increases. Over time, these cycles of dilution and concentration could help encourage complex chemical reactions. One scientist who's explored the energetic conditions needed for life is the British biochemist Nick Lane. Nick Lane studies how energy flows through living systems and how those energy processes might have originated before life existed. Lane and other researchers emphasize the importance of chemical energy gradients in early biological chemistry. An energy gradient occurs when there is a difference in energy levels between two regions. Nature tends to move from higher energy states toward lower energy states, and in the process that movement can power chemical reactions. Living cells today rely heavily on energy gradients across their membranes. In fact, a fundamental biological mechanism known as the proton gradient powers the production of energy molecules inside nearly every living organism. Although early life likely looked very different from modern cells, similar energy gradients may have played a role in the earliest chemical systems that preceded true biology. Tidal environments can create such gradients naturally. When seawater enters a tidal pool and later evaporates, the concentration of salts and minerals changes. Temperature differences between day and night alter reaction rates. Sunlight provides energy for certain chemical processes, while cooler conditions slow others. These constantly shifting conditions may have helped drive a wide variety of chemical experiments. Some reactions would fail, others might produce new molecular structures capable of interacting in more complex ways. Over immense spans of time, these chemical experiments could gradually produce molecules capable of storing information and performing useful functions. Certain environments might have become especially favorable for these processes. Small tidal pools trapped among rocks could act as miniature chemical laboratories. Clay minerals within sediments might help organize molecules into layers. Repeated wet and dry cycles could encourage molecules to bond together into longer chains. Scientists studying the origin of life sometimes refer to this process as prebiotic chemistry. Prebiotic chemistry includes all the chemical reactions that occurred before the first true living cells appeared. One challenge facing early chemistry is the dilution problem. The open ocean is vast, and organic molecules dispersed in such a large volume of water become extremely diluted. When molecules are too spread out, the probability that they will collide and react becomes very small. Tidal pools provide a solution to that problem. They act as natural concentration chambers. Each time water evaporates from a shallow basin, the dissolved molecules remaining in the pool become more concentrated. That concentration increases the likelihood of chemical interactions. Repeated cycles of flooding and evaporation could therefore create favorable conditions for complex molecular assemblies to form. It is important to note that tidal environments are not the only places scientists consider when studying the origin of life. Other hypotheses focus on deep-sea hydrothermal vents, where hot mineral-rich fluids emerge from cracks in the ocean floor. These vents also create strong energy gradients and chemical diversity. Both environments may have played roles at different stages in early biological evolution, but tidal systems offer a particularly intriguing possibility because they combine several useful ingredients. They provide energy gradients. They allow concentration of molecules. They offer cycles of wetting and drying, and they expose chemical mixtures to sunlight and atmospheric gases. In other words, tidal zones create a constantly changing chemical landscape. In such a landscape, nature could run countless small experiments over millions of years. Most would lead nowhere. But occasionally, the right combination of molecules might appear. A structure capable of maintaining itself, a system capable of copying information, a primitive precursor to life. If this hypothesis is correct, then the tides influence not only the movement of Earth's oceans, but also the earliest steps in biological evolution. The quiet rise and fall of seawater may have helped create the environments where life first began to organize itself. Today, tidal environments remain among the most biologically rich regions on Earth. Along rocky shores and shallow coastal flats, countless species live within the narrow zone between land and sea. These organisms still experience the same rhythmic cycles of flooding and exposure that have shaped tidal ecosystems for billions of years. The tides continue to move, just as they always have, and along the edges of the ocean, life continues to adapt to their rhythm. Along the edges of the oceans, there exists a remarkable region where two very different worlds meet. This narrow band is known as the intertidal zone. The intertidal zone is the stretch of coastline that lies between the highest reach of the tide and the lowest level reached when the sea retreats. During high tide, this region is completely submerged beneath seawater. Hours later, as the tide falls, the same area becomes exposed to air, sunlight, and wind. In effect, the intertidal zone exists in two environments at once. It is sometimes an underwater habitat, and sometimes a dry coastal landscape. This constant switching between conditions creates one of the most dynamic ecosystems on Earth. Life in the intertidal zone must endure dramatic changes every single day. Organisms here experience cycles of immersion in salt water, followed by periods of exposure to air. Temperatures may fluctuate rapidly as the sun warms exposed rocks during low tide and cool seawater returns during high tide. Salinity can also vary widely. Rainwater may dilute pools left behind when the tide recedes, while evaporation under strong sunlight can concentrate salts to levels far higher than normal seawater. For many forms of life, these conditions would be extremely stressful. Yet countless species have evolved strategies that allow them to thrive in this challenging environment. The intertidal zone is often divided into several smaller regions depending on how frequently each area is covered by water. The lowest part of the intertidal zone is submerged most of the time and exposed only briefly during the lowest tides. Species living here experience relatively stable conditions compared with those higher up the shore. Farther up the coast lies the middle intertidal zone, which is covered and uncovered twice each day as the tides rise and fall. Above that is the upper intertidal zone, an area exposed to air for much longer periods. Organisms here must tolerate drying conditions and temperature extremes. Each of these zones forms its own ecological neighbourhood, and each neighbourhood supports species that have evolved to survive its particular challenges. Barnacles, for example, are small crustaceans that attach themselves permanently to rocks. Once anchored in place, they open tiny plates in their shells during high tide to filter plankton from the water. When the tide retreats, they seal those plates shut to trap moisture inside and avoid drying out. Mussels use strong protein threads called byssal fibres to anchor themselves to rocks. These fibres act like natural cables, allowing the mussels to remain attached even when waves crash against the shore. Sea stars patrol the intertidal zone as predators, feeding on mussels and other shellfish. Their ability to pry open shells using powerful suction tube feet makes them effective hunters in these environments. Many species of algae, including seaweeds, also thrive here. Flexible fronds allow them to bend with the motion of waves without breaking, while specialized structures help anchor them firmly to rocky surfaces. Together, these organisms form complex communities shaped by the rhythm of the tides. Understanding how these communities function became a major focus of ecological research during the 20th century. One of the scientists who made a profound contribution to this field was the American marine ecologist Robert Paine. Robert Paine conducted influential studies along the rocky shores of the Pacific Northwest during the 1960s. He was interested in understanding how interactions between species influence the structure of ecological communities. During one famous experiment, Paine studied a rocky shoreline where sea stars preyed heavily on mussels. He removed the sea stars from a section of the shoreline and then observed what happened over time. Without the sea stars, the mussel population grew rapidly. The mussels began to dominate the area, crowding out many other species that had previously lived there. The result was a dramatic reduction in biodiversity. From this experiment, Paine introduced an important ecological concept known as the keystone species. A keystone species is an organism that has a disproportionately large effect on its environment relative to its abundance. Even though the species itself may not be the most numerous, its presence helps maintain the balance of the ecosystem. In Paine's experiment, the sea stars acted as a keystone species by preventing mussels from monopolizing the shoreline. Without the sea stars, the entire structure of the community changed. The discovery of keystone species transformed ecological science and highlighted how delicate the balance of ecosystems can be. The intertidal zone turned out to be an ideal place for studying such interactions, because the boundaries between species communities are so clearly visible. The tides themselves help shape these communities by creating distinct habitats along the shore. Lower zones that remain underwater most of the time support species adapted to constant marine conditions. Higher zones favour organisms capable of surviving extended exposure to air. In between, a patchwork of tidal pools forms miniature ecosystems filled with small fish, crustaceans and algae. These pools often become temporary refuges when the tide retreats, trapping marine life until the sea returns. For visitors exploring a rocky coastline, tidal pools can feel like small windows into the ocean. But for the creatures living there, they are entire worlds. Each pool contains a carefully balanced community shaped by the timing of the tides, the structure of the rocks, and the interactions between species. Across the planet, similar tidal ecosystems appear along countless coastlines. From the rocky shores of Scotland to the kelp forests of California and the mangrove fringes of tropical seas, the intertidal zone supports extraordinary biological diversity. Yet all of this complexity depends on one simple planetary rhythm: the rise and fall of the sea. Without the tides, these unique habitats would not exist in their present form. The constant movement of water supplies nutrients, oxygen, and fresh marine life to coastal regions. It also creates the environmental gradients that allow so many different species to coexist in such a narrow band along the shore. Seen from this perspective, the tides are not merely movements of water, they are a driving force behind coastal ecosystems. But the story of tidal influence extends even further, because the tides do not only shape living communities in the present day. Over immense spans of time, the interaction between Earth and the Moon has gradually altered the rotation of the planet itself. The rise and fall of the tides may seem gentle, but over long periods of time, the motion of the oceans has a surprisingly powerful effect on the entire planet. Every day, enormous masses of seawater move across the surface of Earth in response to the Moon's gravitational pull. This motion creates friction between the moving water and the seafloor beneath it. That friction may sound insignificant, but when it occurs across the vast scale of the global ocean, its cumulative effect becomes meaningful. This process is known as tidal friction. Tidal friction gradually removes energy from Earth's rotation. To understand how this works, it helps to imagine the position of the tidal bulges relative to the Moon. If Earth were completely covered by a smooth ocean and rotated extremely slowly, the tidal bulges would remain perfectly aligned with the line connecting Earth and the Moon. But Earth rotates relatively quickly, completing one rotation roughly every 24 hours, while the Moon takes more than 27 days to orbit Earth. Because Earth spins faster than the Moon moves through its orbit, the tidal bulges are carried slightly ahead of the Moon's position. In other words, the bulges do not sit directly beneath the Moon. They lead the Moon slightly as Earth rotates. This misalignment has an important consequence. The gravitational pull between the Moon and the tidal bulges creates a torque, a twisting force that transfers energy from Earth to the Moon. In simple terms, the tidal bulges are trying to pull the Moon forward in its orbit. At the same time, the Moon's gravity pulls backward on those bulges, which slightly slows Earth's rotation. The result is a gradual exchange of energy. Earth loses a small amount of rotational energy, while the Moon gains orbital energy. This transfer causes two long-term changes in the Earth-Moon system. First, Earth's rotation slowly becomes slower. Second, the Moon moves gradually farther away from Earth. These ideas were explored in detail during the 19th century by the British mathematician and astronomer George Darwin. George Darwin was the son of Charles Darwin, the famous naturalist known for his theory of evolution by natural selection. While his father studied biological evolution, George Darwin focused on celestial mechanics and planetary motion. During the 1870s and 1880s, George Darwin investigated how tidal forces could influence the rotation and orbits of celestial bodies. He proposed that tidal friction could gradually alter the relationship between Earth and the Moon over long periods of time. Darwin's calculations suggested that the Moon must once have been much closer to Earth, and that it has been slowly drifting outward ever since. At the time, these ideas were difficult to verify, because precise measurements of the Earth-Moon distance were not yet available. That situation changed dramatically in the 20th century, with the development of lunar laser ranging experiments. During the Apollo missions of the 1960s and 1970s, astronauts placed special reflective devices on the surface of the Moon. These devices are known as retroreflectors. Retroreflectors are designed to bounce light directly back toward its source. Scientists on Earth can fire powerful laser pulses toward these reflectors. The light travels to the Moon, strikes the reflector, and returns to Earth. By carefully measuring the time required for the light to complete this journey, scientists can calculate the distance between Earth and the Moon with extraordinary precision. Light travels at a speed of roughly 300,000 kilometers per second. Because this speed is well known, even extremely small differences in travel time reveal tiny changes in distance. Using this technique, researchers working with organizations such as the National Aeronautics and Space Administration have confirmed that the Moon is slowly moving away from Earth. The rate of this outward drift is about 3.8 centimeters per year. That may not sound like much, but over millions of years, that small annual change becomes significant. Over 1 million years, the Moon would move nearly 40 kilometers farther away. Over hundreds of millions of years, the change becomes enormous. This steady outward motion represents a direct consequence of tidal friction. As Earth loses rotational energy, the Moon gains orbital energy, allowing it to move into a slightly larger orbit. At the same time, Earth's rotation continues to slow. The length of a day on Earth has therefore not always been the same. Geological evidence suggests that hundreds of millions of years ago, a day on Earth lasted only about 22 hours. Going back even further in time, days were shorter still. Some studies of ancient coral fossils suggest that during the Devonian period, roughly 400 million years ago, there were more than 400 days in a year. The number of hours in each day was smaller, so more days were needed for Earth to complete a full orbit around the Sun. This gradual slowing of Earth's rotation continues today. The change is extremely small on human timescales, but it is measurable. Modern observations show that Earth's day length increases by roughly a few milliseconds every century. Although that amount is tiny, it reveals that the Earth-Moon system is still evolving. The tides are not only moving water across the planet, they are slowly reshaping the relationship between Earth and its companion in space. If we look far enough into the future, this process will continue until the Earth-Moon system reaches a new equilibrium. In that distant future, Earth's rotation would eventually become synchronized with the Moon's orbit. At that point, Earth would always show the same face toward the Moon, just as the Moon already shows the same face toward Earth. Such a configuration would represent a fully tidally locked system. However, this state lies many billions of years in the future, long after other changes in the solar system will have reshaped Earth's environment. For now, the slow transfer of energy continues quietly. The tides rise and fall, the oceans move, and with each passing day, Earth's rotation slows ever so slightly while the Moon drifts farther into space. These gradual changes remind us that planetary systems are not static. They evolve across immense spans of time, guided by the steady influence of gravity, and the same tidal forces shaping Earth today are at work across the entire solar system. The tides of Earth can feel like a uniquely terrestrial phenomenon. After all, we experience them along familiar coastlines, watching the ocean rise and fall against beaches and rocky shores. But the underlying physics responsible for those tides is not limited to our planet. Tidal forces operate throughout the entire solar system. Wherever gravity pulls unevenly across a celestial body, tides can appear. Sometimes those tides move oceans of water, as they do on Earth. In other cases, they stretch and squeeze entire worlds made of rock and ice. One of the most dramatic examples can be found around the giant planet Jupiter. Jupiter is orbited by dozens of moons, but 4 of them are especially large and well known. These are the Galilean moons, first observed by the astronomer Galileo Galilei in 1610. Among them is a world named Io. At first glance, Io might seem like an unlikely place to study tidal forces. It is a rocky moon slightly larger than Earth's own moon, orbiting Jupiter at a distance of roughly 400,000 kilometers. Yet Io holds a remarkable distinction. It is the most volcanically active body in the entire solar system. Hundreds of volcanoes dot its surface. Some of these eruptions send plumes of gas and dust more than 300 kilometers above the moon's surface. Rivers of molten sulfur and lava flow across landscapes that are constantly being reshaped. The source of all this activity is tidal heating. Io orbits extremely close to Jupiter, and the planet's gravity exerts enormous tidal forces on the moon. But the situation becomes even more complex because Io is not alone. 2 neighbouring moons, Europa and Ganymede, also orbit Jupiter nearby. Their gravitational influence causes Io's orbit to be slightly elliptical rather than perfectly circular. As Io travels along this elliptical path, the strength of Jupiter's gravitational pull changes slightly during each orbit. This changing gravitational force continually stretches and squeezes the moon's interior. The process is similar to repeatedly bending a piece of metal back and forth. Each cycle generates heat through internal friction. Inside Io, that heat becomes so intense that rock melts, producing vast reservoirs of magma beneath the surface. These reservoirs eventually erupt as volcanoes, releasing the energy generated by tidal forces. In this case, tides are not simply moving water, they are melting rock. Scientists studying these processes refer to the phenomenon as tidal heating. One planetary scientist who has contributed significantly to understanding tidal heating is Francis Nimmo. Francis Nimmo, a researcher at the University of California, Santa Cruz, studies the internal structure and thermal evolution of planetary bodies. His work explores how gravitational forces can generate heat inside moons and planets. Through modelling and analysis, researchers like Nimmo have shown that tidal heating can dramatically influence the geology of celestial bodies. In some cases, tidal heating may even create environments capable of supporting liquid water beneath icy surfaces. One intriguing example is Europa, another of Jupiter's moons. Europa is slightly smaller than Earth's moon, and is covered by a smooth outer shell of ice. Beneath that icy crust, however, strong evidence suggests the existence of a global subsurface ocean. Scientists believe that tidal forces generated by Jupiter's gravity flex Europa's interior, producing enough heat to keep water in a liquid state beneath the ice. This hidden ocean may contain more water than all of Earth's oceans combined. The possibility of liquid water makes Europa one of the most promising locations in the solar system for the search for extraterrestrial life. Another fascinating world is Saturn's moon Enceladus. Enceladus is much smaller than Europa, measuring only about 500 kilometers in diameter. Yet spacecraft observations by the Cassini mission revealed towering geysers erupting from cracks near the moon's south pole. These geysers spray water vapor and ice particles into space, forming a faint ring around Saturn. Analysis of the material within these plumes has revealed salts, organic molecules, and evidence of hydrothermal activity occurring deep beneath the moon's icy crust. Like Europa, Enceladus appears to contain a subsurface ocean maintained by tidal heating. As Saturn's gravity flexes the moon during its orbit, internal friction generates heat that keeps the ocean from freezing completely. In both of these worlds, tides may play a role in maintaining environments where life could potentially exist. The presence of liquid water, chemical energy, and internal heat creates conditions that many scientists consider favourable for biology. Future missions planned by space agencies such as the National Aeronautics and Space Administration and the European Space Agency aim to explore these moons in greater detail. Spacecraft like the Europa Clipper mission will investigate the structure of Europa's ice shell and search for signs of habitable environments beneath it. All of this research highlights an important realization. Tidal forces are not merely a curiosity affecting the oceans of Earth. They are a powerful mechanism capable of reshaping entire worlds. Across the solar system, tides drive volcanic eruptions, maintain hidden oceans, and influence the internal structure of moons and planets. Gravity, acting unevenly across space, quietly sculpts the evolution of celestial bodies. Yet despite these dramatic examples on distant worlds, tides on Earth remain among the most visible expressions of this phenomenon. Our oceans rise and fall each day under the influence of the moon and the sun. In most places the changes are modest, measured in meters rather than mountains of lava or hidden seas beneath ice. But in certain regions of our planet, the geography of the coastline can amplify tidal motion to astonishing levels. In those places, the quiet breathing of the ocean becomes something far more dramatic. Most coastlines on Earth experience tides that rise and fall by a modest amount. In many locations, the difference between high tide and low tide may be only 1 or 2 meters. The change is noticeable but rarely dramatic. Yet in certain places around the world, the interaction between ocean basins and coastline geometry produces tidal ranges so large that the ocean's motion becomes truly astonishing. One of the most famous examples lies along the eastern coast of Canada. Here, between the provinces of Nova Scotia and New Brunswick, the Atlantic Ocean flows into a long narrowing inlet known as the Bay of Fundy. At first glance, the bay appears peaceful, with quiet coastal towns and forested cliffs overlooking the water. But beneath that calm surface, the tides perform one of the most dramatic daily transformations anywhere on Earth. In the upper reaches of the Bay of Fundy, the difference between high tide and low tide can exceed 15 meters. That is roughly the height of a 4-story building. At low tide, fishing boats may rest on the muddy seabed, their hulls tilted against the harbour floor. Hours later, when the tide returns, the same boats float once again as the water rises around them. Entire stretches of shoreline vanish beneath the incoming sea. The reason for this extraordinary tidal range lies in the shape of the bay itself. The Bay of Fundy is long and funnel-shaped, narrowing steadily as it extends inland. When tidal waves enter the mouth of the bay from the Atlantic Ocean, the narrowing geometry forces the water into a smaller space. This concentration of water increases the height of the tide, but the funnel shape alone does not fully explain the phenomenon. Another factor known as resonance also plays an important role. Resonance occurs when a system is driven at a frequency that matches its natural oscillation. A simple example can be found in a playground swing. If someone pushes the swing at exactly the right moment during each cycle, the motion grows larger and larger. The Bay of Fundy behaves in a similar way. The natural oscillation period of water moving within the bay happens to be close to the period of the incoming tidal wave from the Atlantic Ocean. Because these two rhythms are similar, the tidal wave entering the bay reinforces the natural motion of the water already inside it. With each cycle, the wave grows stronger as it travels toward the narrow upper end of the bay. This combination of funnel-shaped geometry and resonance amplifies the tidal range to extraordinary levels. The Bay of Fundy therefore provides a powerful demonstration of how coastline shape and basin dynamics can magnify the effects of lunar gravity. Elsewhere in the world, another fascinating tidal phenomenon occurs where incoming tides interact with rivers. These events are known as tidal bores. A tidal bore forms when a strong incoming tide pushes water upriver against the natural flow of the river. If the river channel is narrow and shallow enough, the advancing tidal wave can form a visible wall of water moving upstream. Instead of a gentle rise in water level, the tide arrives as a travelling wave. One well-known example occurs in the Qiantang River in eastern China. During certain times of the year, the tidal bore in the Qiantang River can reach heights of several meters and travel upstream at speeds approaching 40 kilometers per hour. The wave curls across the river channel like a moving ridge, drawing crowds of spectators who gather along the riverbanks to watch the spectacle. Other tidal bores appear in rivers such as the Severn River in England and the Amazon River in South America. In the Amazon, the tidal bore is known locally as the Pororoca. This powerful wave travels many kilometers inland, sometimes creating a continuous surge of water that lasts for more than half an hour. Surfers have even attempted to ride the Pororoca, traveling extraordinary distances along the wave as it moves through the rainforest. These dramatic events may appear chaotic, but they are ultimately driven by the same gravitational forces that produce ordinary tides along quieter coastlines. The moon's pull sets the ocean in motion. The shape of the coastline determines how that motion unfolds. In regions where the geometry of the coastline and ocean basin amplify tidal waves, the effects can be spectacular. But even in these extreme environments, the underlying forces remain the same. Gravity pulls on the oceans, the water responds, and the shape of the planet guides the resulting movement. Understanding these complex interactions requires precise measurements of tidal motion across the globe. Scientists have long relied on careful observation of tides to build accurate models of ocean behavior. For centuries, these observations were made using simple tide gauges placed along coastlines. Today, however, the study of tides has expanded far beyond the shoreline. Modern technology allows researchers to measure the height of the ocean across the entire planet with extraordinary accuracy, and from space, satellites now watch the slow breathing of the oceans as it unfolds across Earth's surface. For most of human history, our understanding of the tides came from observations made along coastlines. Harbour masters placed measuring staffs in sheltered bays. Mariners recorded water levels as they rose and fell against docks and stone piers. Tide tables were built from years of patient measurements taken at specific locations. These records were incredibly valuable, but they had an obvious limitation. They only described the tides at the places where measurements were taken. The open ocean, covering more than 70% of Earth's surface, remained largely unmeasured. Scientists could infer how tides behaved across ocean basins using mathematical models, but direct observations from the middle of the sea were extremely difficult to obtain. Ships could measure local water levels, but those measurements were temporary and limited to narrow paths across the ocean. For a long time, the full global pattern of the tides remained partly hidden. That situation changed dramatically during the late 20th century, with the development of satellite altimetry. Satellite altimetry is a technique that allows scientists to measure the height of the ocean surface from space. The method is surprisingly elegant. A satellite orbiting Earth carries a radar instrument that sends pulses of microwave energy toward the ocean surface. These pulses travel downward at the speed of light, reflect from the water, and return to the satellite. By measuring the time required for the radar signal to make the round trip, scientists can calculate the distance between the satellite and the ocean surface. Because the satellite's orbit is known very precisely, this measurement reveals the exact height of the ocean at that location. The accuracy of modern satellite altimeters is remarkable. they can detect changes in sea level of only a few centimeters across the vast surface of the global ocean. One of the pioneering missions to apply this technology to oceanography was the satellite known as Topex Poseidon. Launched in 1992 through a collaboration between the United States National Aeronautics and Space Administration and the French Space Agency Centre, National d'Études Spatiales, Topex Poseidon was designed specifically to study the oceans. Its instruments repeatedly measured sea surface height across nearly the entire planet, building an unprecedented global map of ocean topography. Although the ocean might appear flat from a distance, it actually contains subtle hills and valleys created by currents, temperature differences, and tidal motion. These variations may measure only tens of centimeters in height, yet they reveal important information about how water moves across the planet. The success of Topex Poseidon led to a series of follow-up missions known as the JASON satellites. JASON 1, JASON 2, and later JASON 3 continued the work of measuring global sea level with extraordinary precision. Together, these missions created one of the longest and most detailed records of ocean height ever assembled. One of the scientists closely associated with the development of satellite altimetry is oceanographer Li Luangfu. Li Luangfu, working at the Jet Propulsion Laboratory in California, played a central role in designing the altimeter instruments used in these missions. His work helped transform satellite observations into a powerful tool for studying the oceans. Through these measurements, scientists could observe the subtle rise and fall of the ocean surface caused by tides across the entire globe. Instead of relying only on coastal tide gauges, researchers could now track tidal waves as they moved through open ocean basins. The data revealed patterns that had once been predicted mainly through theory. Amphidromic systems, rotating tidal waves, and basin-scale oscillations all became visible in satellite maps of sea surface height. Scientists could watch tidal waves propagate across thousands of kilometers of ocean, bending around continents and interacting with underwater ridges. For the first time, the global breathing of the oceans could be observed directly. Satellite altimetry also allowed researchers to refine models of tidal motion with far greater accuracy. These models help predict tidal currents, coastal flooding, and ocean circulation patterns. Accurate tidal predictions are essential for navigation, offshore engineering, fisheries management, and coastal planning. They also play an important role in climate science. Because the oceans absorb and transport vast amounts of heat, understanding how water moves through the global ocean is critical for predicting long-term climate behavior. Satellite measurements have shown that the oceans are not static reservoirs of water. They're constantly shifting under the influence of gravity, winds, temperature differences, and planetary rotation. The tides are one part of this complex system. Seen from space, the tides appear as enormous waves sweeping across the planet in predictable patterns. Their motion reflects the gravitational influence of the Moon and the Sun combined with the shape of the ocean basins and the rotation of Earth itself. Yet even with the help of satellites, the tides remind us that the Earth-Moon relationship is still unfolding. The same gravitational forces that move the oceans today are slowly altering the distance between our planet and its companion in the sky. Over immense spans of time, that relationship continues to evolve. When we think about the Moon's influence on Earth, the most obvious effects are the tides. The oceans rise and fall each day under its gravitational pull, creating the rhythmic motion that has shaped coastlines and ecosystems for billions of years. Yet the Moon's influence reaches far beyond the oceans. In quiet and subtle ways, it may also help stabilize the entire planet. One of the most important properties of Earth is its axial tilt. Earth does not spin perfectly upright as it orbits the Sun. Instead, its axis is tilted by about 23½ degrees. This tilt is responsible for the changing seasons. When the northern hemisphere tilts toward the Sun, sunlight strikes that part of the planet more directly, producing warmer temperatures and longer days. 6 months later, the situation reverses, and the southern hemisphere receives more direct sunlight. Without axial tilt, Earth would have almost no seasonal variation. But the tilt itself raises an interesting question. Why does Earth's axis remain relatively stable? The gravitational influences of other planets in the solar system can gradually perturb a planet's rotation. Over long periods of time, these influences can cause the tilt of a planet's axis to wobble, or even change dramatically. This phenomenon is known as axial precession and obliquity variation. A familiar example can be found on the planet Mars. Mars currently has an axial tilt somewhat similar to Earth's, about 25 degrees. However, computer simulations show that Mars's tilt can vary widely over time, swinging between angles of roughly 15 degrees and more than 45 degrees. Such dramatic changes can have major consequences for climate. When the tilt becomes larger, the poles receive much more sunlight during summer, potentially melting polar ice and altering atmospheric circulation. When the tilt decreases, polar regions receive less sunlight and become colder. Mars may therefore experience extreme climate swings over geological timescales. Earth appears to be far more stable. While our planet's axial tilt does vary slightly over tens of thousands of years, the changes are relatively modest. The tilt typically fluctuates between about 22 and 24.5 degrees. One reason for this stability is the presence of the Moon. The Moon's gravitational influence exerts a stabilizing effect on Earth's rotation. By interacting with Earth's equatorial bulge, the Moon helps regulate the precession of Earth's rotational axis. This stabilizing influence reduces the likelihood that Earth's tilt will wander into extreme ranges. Astronomer Jacques Lasker has studied these long-term orbital dynamics in detail. Jacques Lasker, working at the Paris Observatory, used powerful computer simulations to investigate how planetary orbits and rotations evolve over millions of years. His research showed that the presence of a large moon can significantly stabilize the axial tilt of a planet. Without the Moon, Earth's tilt might behave more like that of Mars, drifting unpredictably over time. Large variations in tilt could produce dramatic climate changes, potentially making Earth's environment far less stable. Instead, the Moon acts as a kind of gravitational anchor for Earth's rotational orientation. This stability has likely played an important role in the development of life. Stable climate patterns allow ecosystems to evolve gradually. Organisms can adapt to predictable seasonal cycles rather than facing sudden and extreme environmental shifts. The Moon therefore contributes indirectly to Earth's long-term environmental balance. The tides themselves also play a role in maintaining planetary systems. By moving water through ocean basins, tides help drive mixing within the oceans. This mixing distributes heat, nutrients, and dissolved gases across the global ocean. Ocean circulation patterns influence atmospheric conditions, weather systems, and long-term climate behavior. Tidal mixing also helps regulate the distribution of nutrients essential for marine ecosystems. Without these processes, certain regions of the ocean might become stagnant or depleted of key resources. In this sense, the tides function as part of Earth's environmental circulation system. They help keep the oceans active and interconnected. The Moon therefore acts not only as a gravitational partner, but also as a quiet regulator of planetary processes. It shapes the tides. It influences the length of Earth's day. It helps stabilize the planet's rotation. And through these effects, it contributes to the environmental conditions that allow life to flourish. All of this occurs silently. The Moon does not announce its presence with dramatic displays of power. Instead, its influence unfolds slowly through gravity, acting steadily across billions of years. Each night it rises above the horizon, appearing calm and distant. Yet beneath that tranquil appearance lies a powerful relationship between two worlds. Earth and the Moon move together through space, bound by gravity and connected through tides, rotation, and orbital motion. The oceans respond to that connection every day. Their gentle breathing reflects the presence of a companion that has guided Earth's evolution since the earliest days of the solar system. And when we watch the tide move along a shoreline, we are witnessing only a small part of that larger story.